My name is Mark Dale. I'm going to give you a quick tutorial on how to use the Comet Bead Motility simulator on OS X. So we provide a disk image file that I've downloaded to the desktop here, which contains a precompiled binary for Mac OS X. You may also want to check the website, which may have a more up-to-date version than the one that's included with the paper. So I've downloaded to the desktop here. If I double-click, it'll mount it. And you can see that the disk image contains the Comet executable, a directory which is the source code from which that was compiled, a Comet parameters file which is a text file which contains the settings that the executable reads in, that tells the executable what you want it to do, and a readme file that describes the other files and has some licensing information. So to run the program we need to create a directory on the hard drive that will allow us to write to it. So the disk image is read-only, so we need to move some of these files across to the hard drive before we can run them. So to do that I'm going to open up a terminal, which you can do by going to Spotlight and typing in terminal. And so I'm going to create a directory called Comet, and then move into that directory. So mkdir creates the directory, cd changes to that directory. I'm going to open that directory in the Finder, make it a little easier to copy the programs across. And I'm going to copy across the executable and the Comet parameters file. There we go. So here's a copy of these two files which are on our hard drive now, and that's in this directory. So to run it with the default parameters, all I need to do is /comet2, where the / is because we're running an executable in our current directory. If we move the Comet program to somewhere in our path, we could just call it from wherever just by typing Comet. And the 2 is because we wanted to use 2 CPUs. So it takes, when it's doing a calculation, it takes one parameter. That parameter tells it how many threads to run, because it can run in a multi-threaded way to make it run a bit faster. And I'm running on my laptop, which has 2 CPUs. So if I hit return, the first thing it does, it asks me whether whether I'm ready to do the calculation. It says clear directories and start run. So I say yes, and then it's off calculating a new simulation. And I'm not going to go through all the details about what it's producing on the screen here, but it's basically giving a little bit of an idea of how the calculation's going. You can look at things like the distance the nucleator's moved, and the frame number. So the Comet parameters tells the program it should be doing 700 frames, and it'll tell you that this is the current frame that it's on is say 25, etc., etc. Okay. So while that's running, I'm going to start up a new terminal window, and as you can see, it takes a little while for this to run. We're only on frame 29 of 700 so far. So I'm going to go to one that I calculated earlier, and I'm going to use that to demonstrate a quick view of some parts of the network. So if I open this directory in the Finder, you can see that as it runs, the program creates a number of directories. The bitmap directory contains projections of the network, as though the bead might be viewed from as you might see it in the microscope. So you can see here this is before symmetry breaking at frame 113. And then if we go to say frame 200, it's after symmetry breaking, and then sort of way down the line you can see after it's moving off there. And we also have projections from different directions. So the one that I was just showing you, these are X projection, and there's also Y projections, which and Z projections, which are obviously from the orthogonal views. The program actually calculates the position of the camera based on the direction of the symmetry breaking and the direction that the shell's opening. And so the X projection should be its best guess at what's going to show you a good view of the symmetry breaking. Okay. The data directory contains all of the snapshots of the network, all the information that the program has about the network at that time. And you can use these data files to restore the run from particular time points. And also when you go in and you might want to rewrite the data, you might want to change the way it was displayed, the program will read these data files in and then can output bitmaps or 3D data or whatever you need it to do. And that's another thing I want to show you. I want to show you the 3D viewing, which is actually very useful for understanding what's going on during the motility. And so we can do that by running the Comet program and typing in, rather than a number which tells it the number of CPUs to do the calculation with, we type in view and then a frame range. And for the interactive view, we want that frame range just to be one frame, so 200:200. And then what the program's going to do, it's going to open up a three-dimensional view window on the left here. And it's going to allow us to have an interactive view of the network. So here we go. And as I mentioned, it's positioned the camera in a way that it thinks is going to be a good view of the bead, showing the shell opening up here. And if I click on this window, I can click and I can drag, and then I can actually interactively move this network around. And I can zoom in and take a look at the network in detail. The number of parameters, again in the Comet parameters file, that tell the Comet program how to display it. And the current settings say that we want it to display just the links, so we're not displaying the nodes, and we're not displaying any isosurfaces. And isosurfaces are just surfaces that show you the densest areas of the network, and that can be useful to show the shape of the dense area in the tail. This is just showing where the links are and the strain in those links. And you can see here that what we've got is the symmetry breaking actually occurs in one dimension. We mentioned this in the paper. So it's kind of flat in this direction, and it's much wider in this direction. And that there's a crack opposite the direction that the bead's moving off. And this kind of is something that we mentioned in the paper as well. And also the strain that's building up around the edge of the network here, and in this crack, you can see that quite well. Okay, so this is a very useful view, and you can also use that view while the program's running. So if I just go back to the original directory, so now I'm in this directory here that this run is still going on, and I can do the same thing. I can do Comet view, and so up here we've got to frame 60, so let's do 60:60, and you can actually use that even before the run is complete to take a look at how things are going and what stage we've got to. So you can see here more or less symmetric network here, strain building up on the outer links. Those links are largely sort of yellow and orange, the ones where the strains build up, and the links in the middle are largely blue. And this is quite useful to be able to see what's going on without actually sort of having to kind of guess from the bitmap view. And the other thing that I also want to show you, which I think I'll show you in a separate tutorial, is the isosurfaces. And so that's it. You can see that this thing's going doing its calculation here. If you want to quit, you just hit the letter Q, and it comes up with this thing that says abort run. And if I hit yes, it'll stop it. Otherwise, you know, it'll carry on and do the rest of the run. Okay, thanks very much for listening.